Yeah.
And then either art, but if art's at a bad time, so
Okay.
I don't know.
So they're not gonna make you take a core.
Yeah.
Okay, that's good then, because I don't think you want to do a core there, do
No.
you? Yeah, I don't imagine that. So I'm so excited to do that. Yeah. Well, excellent. All right, cool. Tell your mama I said, hey, no problem. Let me turn this other one on. Do.
Yeah, Jack, before we leave, we need to figure out what order to put everything in.
Are you coming back today?
I can't do it, but I can stay for a little bit.
I also have to go, like at work.
Okay,
She gotta work.
So.
it should only take a few minutes. I won't grab coffee, grab the button. So, I'll save it for next week.
Aren't you at Brewster's? Is that where you are?
Also, what happened to brownies?
Oh, yes, I have them. I'll get them for you in just a minute. Thanks for the reminder. Yeah, y'all earned brownies.
Okay.
Oh, Lily just left before she got her brownie.
You still have meteoroids flipped
On where?
on English study guide.
Oh, really? Okay.
I Googled to make sure, but they're flipped.
Okay, thanks for catching that.
I was very confused.
Yeah, no, that would be me.
Study guides to another.
Yeah.
On other.
No, that's a definite brownie point.
I don't want you to have sugar,
Yeah.
so I'm not gonna tell you.
You're like, I'm looking out for number one.
I found that these 10 different like spelling or.
Oh, there are probably a ton in there because they came right out of the stuff. Let me get the brownies.
Track down every last thing.
Video. It's like one of the videos that haven't been caught.
I will go through every last one of everything. On my brand.
All right, let me grab.
I go out on the walls and destroy the planet.
What?
You have fun doing that, I bounce on the walls and destroy the planet.
Alex, we'll support you from a distance. We'll support you
There
from
is no
Pluto.
safe distance.
We'll support you from Pluto.
All right, here's your brownies. If you want your brownies, use the hand sanitizers. There are, well, with Yusuf and Lillian out, everybody can have a whole one. There's a half of one like we usually do. They're cold, they're in the fridge. These just have cream cheese, this is what Walmart sent, and these have chocolate. That's what Walmart sent. I haven't got anyone, that's my lunch. Yeah.
Well, thank you for knowing me.
Lily left before I got a chance to give her brownies. Sorry, Lily.
Hey, Leah.
All right, what have I got to hand out real quick?
Wait, you wanna trade?
No.
It's just
Okay, I'll take it.
I'm just taking the tray, there's only one left on it.
There you go.
Oh, thank you. Don't get this.
I have extra copies of your lab 24, your electric car lab. Some of you took a copy and some of you did not. We handed in one for team. So I have them. If you want them on your way out today, grab them. That way you have a copy for your binder. And then got a couple more things to hand out that people either left or weren't here. Shoot, throwing stuff. Yeah, Alex, you left that. And this stuff is not here. Is where's the? Did it really in one piece?
Yeah.
Oh.
No.
Yeah, this is your two. Okay, so it's more Yusuf stuff. Yusuf. I gotta send it down. Who's this? That's somebody. Milo. Milo, this is what I'm got that. Where Yusuf, Yusuf did everything from last week through the end ahead of time, and he got it all done. Drew, So he worked real hard, did everything early. James, you go. Sorry. Not here. Yusuf again.
What you doing there, man?
Jack.
What do you think I was doing?
Jack.
Nothing, I was just wondering what you were doing.
Hello.
Why were you insinuating I was insinuating anything? That's a weird insinuation.
Hand it over your head, like you're not sitting there right in front of me.
Snacks, unidentified white liquid.
Bailey. Alright,
I'm eating.
here you go.
Yes.
So Jack, you get to be jealous of Cole now because he will be spending the next 4 years at Baylor, home of Dr. Pepper.
Oh.
Yeah. So Cole, you might have to put Jack in your suitcase so he can get all the Dr. Pepper on campus.
Can you smuggle me to Texas? Think you could smuggle me there? Like this? Air holes, I don't need much, like two.
Apparently they get like free Dr. Pepper every Friday, is it? I don't know.
I think it's Wednesday.
Wednesday, it's just,
Yeah, no, that's because they have a Dr. social hour,
Wow.
and apparently if you get enough of
I guess
it.
now I should go to Baylor.
they put you where? On a plaque if you drink enough?
I'm going to Baylor and I'm getting my.
Jack's decided on his college decision now. All right, there we go. Okay. Well, baby.
That's one of the easiest decisions I've ever made, to be honest.
All right,
Easier.
Last-
One.
lesson.
I'm good.
Yes, ma'am.
He was really tall.
I was surprised. I'm like, no, she got that wrong. That's hilarious. But yeah, I mean, that's why I know you're tall, but that's funny. That's hilarious. Oh my gosh. Well, some people in here were weighing like 220 pounds and stuff. I was like, for real? Okay. Mm-hmm. Alrighty, so last lesson. Next week, we're gonna do a review first. And when we have reviewed to satisfaction, I have kind of a lab. I'll say it's kind of a lab, it's kind of a craft. And that will be for fun.
Crab.
Not a craft. All right. So here we go. So we have all these stars, universe, beyond the universe, poof, poof. Now, the way we end up doing this last unit here is we kind of blend it in with the final because you don't get a separate unit test. So there isn't as much from this unit on the final. There's some, but not quite as much. So we have variable stars that are located in diagonal. Does anybody want to try this word? Do we know this word?
Which one?
The fun one. This one.
I got one.
You want to do it?
Where is it?
Pretty much, yeah. Hertzsprung Russell diagram. They pulsate in brightness because of expansion and contraction. And we'll look at a picture of it in a minute. So discovering our Milky Way. This is our galaxy, right? So we have types of variables, and the relationship between a star's luminosity and its pulsation period is kind of how we categorize them. Put the pillows down. So what do we call the type of star that has the same luminosity and a pulsation period of 1.5 hours in one day? Do we know what this one is? This one is, these are these RR Lyrae variables, okay? This is not on your exam. Be aware of it. I don't know. I don't know. I don't know what that one is. Definitely look that up. Ronald Reagan. It could be Ronald Reagan. Mm-hmm. All right. So what's this next one? Jack, do you know?
No, it's Y.
Yeah, cepheid variables, right. There you go. Cephalopods.
English well, okay?
That's all right. We don't all English well. So these have the luminosity that can double from dimmest to brightest, and they have a pulsation period of 1 to 100 times, 1 to 100 days. And this last one is, anybody got it? Liam, what you got? Yeah, galactic center. It's a region of high star density at the center of the galaxy. Boom. Yep.
Black hole life.
No. So when we get to the shape of the Milky Way, and we have to map it out, and galaxies have different shapes and whatnot, but we discover it by mapping with what? What do we map these galaxies with? What are we using? What kind of technology? Do you know? There you go. Radio waves. Simple radio waves. Stuff we've been using for years and years and years. We're still using it because it's effective. So we have a nuclear bar or bulge, and that surrounds your galactic center. And the Milky Way is what we call a barred bulge. Isn't that attractive? A barred bulge. I don't like that term at all, but that's what it is. Yeah. And then we have, there's nobody asking to get in, right? Okay. And then where do you find the oldest stars and the youngest stars? We know? You know?
The oldest stars bar.
That's right. So the bulge has the older stars and the bar has the youngest stars. And that has to do with with sort of the way you'll see in a second when we look at a picture of it. But the further out they are, the older they are. We have some kind of disk, flat distribution of stars, interstellar matter, and spiral arms and a plane of the galaxy. What you get, Caitlin? Yeah, galactic disk. Okay, there you go. See, these are easy, and these are not on your exam, but just know them. And what surrounds a nuclear bulge in a galactic disk, Jack?
Halo?
There you go, a halo. Ah, see, this is just like straight from your notes, right? So what is elongated curved spiral sections that are connected to the center of the galaxy, mapped using hydrogen emission spectra? Ooh, fancy schmancy. Okay, Caitlin, you go. There you go, arms. Okay, so when you think about a galaxy and you think about like, you know, sometimes you can picture them in your head and you see the big spiral thing with the little arms reaching out. That's what we're dealing with. So in a minute, we're gonna look at some pictures of different shapes and you'll see. So the mass of the Milky Way. So the massive stuff located within the sun's orbit is approximately 1 billion times the mass of the sun. That's everything within the sun's orbit, not just like the planets. The mass of the halo is what, Jack? 90% of the mass is galaxy. And where did we just say the halo was? Is it in the middle? It's on the outside, so all the way out, yeah, way beyond where we are.
I think I figured out why it's
Okay, why is it RR?
it goes like AA, AB.
Ah, okay.
R word I can't say
Mm.
was the first star and R was the 10th variable.
There you go. Okay. She can't say it. Want to attempt it?
I can't say it.
Let me see it. Probably really fun. Oh,
Yeah.
Coronae borealis.
I
Okay,
can't
R
see
Coronae
it.
borealis. All right. So the halo is 90% of the galaxy's mass. We don't even, like, that's not where we are. We're way in the middle, right? So then you have this galactic black hole located at the center. This is what Drew was just talking about, of most galaxies. And mass is millions to billions times that of the sun. And Sagittarius A is a point around which what rotates, Drew?
Oh, I was just gonna say something about black holes. So black holes have this part called the event horizon.
Mhm.
That's the part that you can't go past.
Mm-hmm.
But recently, only like 2 months ago, we filmed two black holes, we didn't film it, but they captured two black holes colliding with each other.
Oh,
They
I didn't see
collided
this.
with each other, and they collided with more energy than all of the stars in the universe combined.
Wow, I did not catch that news. That's interesting. So this picture here,
Sorry, and they turned the radio waves into sound waves to make
Oh.
what it would sound like if it was on Earth.
uh-huh,
And it sounded like
Hmm. weird. Huh. So this picture here, this is the first image of a black hole. Like, we know they're there, but weren't able to get an image of them. And this came out, I want to say 2 or 3 years ago. And it was basically what it was is they got all the data and it was non-visual data. And then they used computer program to translate it into visual data so that you can actually see it. And that's what they've done with like a lot of the very distant stuff that we can't see. We collect the data and then we convert it into something we can recognize. So it looked kind of like that. And there's some really interesting interviews. The lady, the scientist that kind of put it all together in the end talks about, you can find interviews on, guys, you can find interviews on YouTube and stuff, but she talks about how, you know, how long it took and what methods she used. And it's pretty cool. Yeah.
Why? Because there may be black holes like super close to us.
Mhm.
It is, you can't see them
Mhm.
because the light sucks into them.
Yeah.
So the only thing you can see is
Bless
how they affect the universe around it.
Right.
And
Exactly.
you can see the dispersion of light,
Mhm.
So you can't actually see the black.
Exactly. So you can see the effect it's causing, but you can't actually see it. And this was the first time they were able to develop some sort of image. It was really big news when it came out. It was like international news. It was a big deal. So what is located in the disc and arms and have small amounts of heavy elements? What'd you get, Jack?
Population 1 stars.
Population 1 stars, okay? And what is located in the halo and bulge and have even smaller amounts of heavy elements? Yes. Population 2 stars. Okay, so now we have names for things. All right. So how did this get here?
That's why.
Formation. So it began, this is what we believe. The Milky Way began with what? A cloud in space. What are we looking for here? Do we know? Jack, do you know?
Oh.
Yeah.
Spherical cloud.
Yeah, spherical cloud in space. Okay, so this is as far as science can get us. There was some big spherical cloud. Where'd it come from?
Nobody knows.
Nobody knows. That's as far as we can go.
Once they get like.
Mhm.
Go and get time machines. you can actually-
That would be interesting,
you can go
yeah?
back
Right,
and see
right.
where everything-
Well, if we go back in time, it has to be to November 5th, 1955, because that's when, you know, Marty's parents meet and November 5th, 1955 is when, yes.
Do it, if we didn't see ourselves show up then how do we know that you'll ever get?
Right.
confirmation?
Right.
You know, you would have had some sort of know,
Mhm.
bad.
Right, exactly.
National, the big disasters may never happen.
Mm-hmm.
Just remember.
What were you gonna add, Drew?
with the past.
Two things, first of all, it actually is possible, like actually possible to travel into the future.
Okay. Yep. Shh. Hang on, guys. Uh-huh. Yeah, guys.
So we can stop by.
Uh-huh.
And the other thing, it's actually possible to get a live view of Earth from the past. If you travel out half a light year, you place a massive mirror, focus at the Earth,
Mm-hmm.
the light that travels from the Earth takes half your hit the air, and half your come back.
Right. So we're actually going to talk about some of this theoretical stuff in a little bit. Well, I know, but we haven't done it. So yeah. So yeah, when you get into space and time, then you get into this whole space-time continuum business, the final frontier. And this is really like, of course, astrophysics, but there are people that spend their life trying to figure out, you know, what really is time? Is there a way to manipulate time? You know, and yeah, there is, like, depending on how fast you travel, there is some manipulation of time. And we'll talk about that a little more next year in physical science, but do what? Gravity? Yes. So speaking of gravity, this cloud is going to collapse under its own, Jack,
Gravity.
under its own gravity. Speaking of gravity, yeah, it's going to collapse under its own gravity. So you got this big cloud, here it gets dense and it collapses under its own gravity. And then you get rotation and it gets squashed into this disc shape. And then we have spiral arms. We have no idea how those big spiral arms hang on. Yeah. That's the best we got. Yeah, pretty much that. Like, it's probably hanging on there. So one hypothesis that regions of alternating density and rotate in a rigid pad. What's this one? Do we know, Piper?
Spiral density way.
Yeah. Okay. So yeah, this is one hypothesis. Well, maybe this is going on. Where are you over here? I keep losing you today. Oh, Piper. There. I don't know why. Okay. So yes, this is hypothesized that the arms are not permanent, but continually forming as a result of disturbances evidenced by broken spiral arms, which we've seen. And it's hypothesized that the arms are only visible because they contain hotter, brighter blue stars. Well, this is all hypotheses, right? We don't know for sure. You guys good back there, Chloe, Milo? Milo, why don't you swing your chair around the other side so you're there? Because yeah, there's no Parker. That way, you're not back to the screen. So yeah, so we don't really know, but we hypothesize that maybe they're not permanent. So if they're not permanent, we're never going to see that change, right? Because we're talking millions and billions of years to see a change, and we haven't been able to record data for anywhere near that long.
It could change like in next.
It could. So, but we would not notice it because it would be so slow is the thing. So this is really cool. This shows you basically what we just talked about. So this is a simulation of the formation of the Milky Way galaxy, and it had no sound, so I added some fun sound for you. I'll give you volume again though. Hang on a sec. Pause it. My computer had its volume down. Well, it should be giving you a song. Wait a sec. Hang on. You're giving me trouble. Come on. Yes. Aha. I see the problem. Nope. Boom. Yeah. Ding, 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 ding. We hear you. All right. So put this back up. Here you go. This is really kind of it's a little slow, but you get the idea. Kind of captivating. So raise your hand if you know who is singing. Oh, raise your hand if you know the name of the song. You know the name of the song? The three of you know the name of the song? Okay, wait a minute. Say it at the same time. What's the name of the song? Ooh, I give you both an extra credit point for your class participation. Space Oddity, David Bowie. Yep. Does anybody know what he called himself during this period of his life? Ziggy Stardust? Oh yeah, go look up some pictures of that business. Woo! Yeah. Hang on, Drew's talking. Liam? Uh-huh.
Galaxies where there is just nothing, it's just completely black.
Nothing.
And people don't really know why it's there yet, because gravity should have pushed it together.
Right.
But Einstein's theory of general relativity actually does allow for an entity called a white hole
A white hole. What's a white hole?
Instead of a black hole.
Yeah.
Instead of pushing everything in, it's absolutely everything away from it.
Okay.
It has negative gravity.
Hmm.
And that's what some people believe is in the center of these like massive just.
Very interesting. We're going to talk about nothing in just a second. So when discovering other galaxies, we have our buddy Edwin Hubble.
Fish.
Yep, there's a fish. In 1927, he discovered what nebula was actually a galaxy. James, is that your hand? Not your hand. All right, Liam, you go. Andromeda. That's it. All right, and properties of galaxies. Tell me about their mass and their luminosity. Who knows? Piper?
Wait, variable?
Okay, that's what you're going for. James, Chloe, you guys good? So yes, variable mass, variable luminosity. And what subatomic particle interacts weakly with other matter found in all galaxies? Oh, Drew. Dark matter. Okay, what the heck is this? Now I want you to keep in mind, we're gonna watch a video. Hang on, we're gonna watch a video. I want you to keep something in mind, and you may not have really thought about this before, but try to picture the image of an atom, any atom, okay? Doesn't really matter. And you know, we can't really accurately depict it, right, in a 3D image because we know that the electrons move in different patterns depending on their shell, and they're more like this busy cloud, okay? What's in between the nucleus and the moving electrons? What is that? What is it?
Gravity.
Gravity, but what's there?
It's theoretical, but it's
Mhm.
that's what people consider to be dark matter, but at the same time, it's what a lot of people think dark matter is that it's gravity in between the atom.
In between particles, right?
So we can have orbits.
Most of an atom is quote unquote empty space, which really isn't a thing. Like we think about physics and physical science, and there's nothing really empty. Like even if you see a glass, right? Half of it's water, half of it's air, if it's half full or half empty. Like this space is not empty. There's stuff everywhere. But most of what makes up an atom is empty space. You are mostly empty space. So keeping that in mind, dark matter. This is a fascinating thing. And we gotta love some TED Ed videos, right? Because they're great. Ah, true.
Ancient Greeks had a great idea. The universe is simple. In their minds, all you needed to make it were four elements: earth, air, fire, and water. As theories go, it's a beautiful one. It has simplicity and elegance. It says that by combining the four basic elements in different ways, you can produce all the wonderful diversity of the universe. Earth and fire, for example, give you things that are dry. Air and water, things that are wet. But as theories go, it had a problem. It didn't predict anything that could be measured. And measurement is the basis of experimental science. Worse still, the theory was wrong. But the Greeks were great scientists of the mind, and in the 5th century BC, Lucifer of Miletus came up with one of the most enduring scientific ideas ever. Everything we see is made up of tiny, indivisible bits of stuff called atoms. This theory is simple and elegant, and it has the advantage over the earth, air, fire, and water theory of being right. Centuries of scientific thought and experimentation have established that the real elements, things like hydrogen, carbon, and iron, can be broken down into atoms. In Lucifer's theory, the atom is the smallest indivisible bit of stuff that's still recognizable as hydrogen, carbon, or iron. The only thing wrong with Lucifer's idea is that atoms are, in fact, divisible. Furthermore, his atoms idea turns out to explain just a small part of what the universe is made of. What appears to be the ordinary stuff of the universe is, in fact, quite rare. Lucifer's atoms and the things they're made of actually make up only about 5% of what we know to be there. Physicists know the rest of the universe, 95% of it, as the dark universe, made of dark matter and dark energy. How do we know this? Well, we know because we look at things and we see them. That might seem rather simplistic, but it's actually quite profound. All the stuff that's made of atoms is visible. Light bounces off it and we can see it. When we look out into space, we see stars and galaxies. Some of them, like the one we live in, with beautiful spiral shapes spinning gracefully through space. When scientists first measured the motion of groups of galaxies in the 1930s, and weighed the amount of matter they contained, they were in for a surprise. They found that there's not enough visible stuff in those groups to hold them together. Later measurements of individual galaxies confirmed this puzzling result. There's simply not enough visible stuff in galaxies to provide enough gravity to hold them together. From what we can see, they ought to fly apart, but they don't. So there must be stuff there that we can't see. We call that stuff dark matter. The best evidence for dark matter today comes from measurements of something called the cosmic microwave background, the afterglow of the Big Bang. But that's another story. All of the evidence we have says that dark matter is there and accounts for much of the stuff in those beautiful spiral galaxies that fill the heavens. But where does that end? We've long known that the heavens do not revolve around us,
Cool.
and that we're residents of a fairly ordinary planet, orbiting a fairly ordinary star, in a spiral arm of a fairly ordinary galaxy. The discovery of dark matter took us one step further away from the centre of things. It told us that the stuff we're made of is only a small fraction of what makes up the universe. But there was more to come. Early this century, scientists studying the outer reaches of the universe confirmed that not only is everything moving apart from everything else, as you'd expect in a universe that began in a hot, dense Big Bang, but that the universe's expansion also seems to be accelerating. Either there's some kind of energy pushing this acceleration, just like you provide energy to accelerate a car, or gravity does not behave exactly as we think. Most scientists think it's the former, that there's some kind of energy driving the acceleration, and they call it dark energy. Today's best measurements allow us to work out just how much of the universe is dark. It looks as if dark energy makes up about 68% of the universe, and dark matter about 27%, leaving just 5% for us and everything else we can actually see. So what's the dark stuff made of? We don't know, but there's one theory called supersymmetry that could explain some of it. Supersymmetry, or SUSY for short, predicts a whole range of new particles, some of which could make up the dark matter. If we found evidence for SUSY, we could go from understanding 5% of our universe, the things we can actually see, to around a third. Not bad for a day's work. Dark energy will probably be harder to understand, but there are some speculative theories out there that might point the way. Among them are theories that go back to that first great idea of the ancient Greeks. The idea that we began with several minutes ago, the idea that the universe must be simple. These theories predict that there is just a single element from which all the universe's wonderful diversity stems, a vibrating string. The idea is that all the particles we know today are just different harmonics on the string. Unfortunately, string theories today are as yet untestable. But with so much of the universe waiting to be explored, the stakes are high. Does all this make you feel small? It shouldn't. Instead, you should marvel in the fact that, as far as we know, you are a member of the only species in the universe able even to begin to grasp its wonder, and you're living at the right time to see our understanding explode.
So yeah, you're mostly dark. You're so dark. Did you know that? You're dark people. It's a weird thought, right? Like you probably never, if you've never really considered it before, it's a very strange thought. Like, what in the world am I made of, right? All right, are we good over here? Everybody's good back there too? All right, so other galaxies in our universe. So classification of galaxies. What types of galaxies have both normal spirals and barred spirals? Do we know what kind, Liam? Okay, good. So we have these suckers right here, these little disc-like ones. That's so pretty, a little flat like a disc. And what are our other two? Do we know what the other two types are?
High explosives.
Caitlin? Yeah, okay. So yeah, elliptical or irregular, normal and barred. Yeah, these are these guys here. Normal and barred are the disc-like ones. And then we have elliptical and these irregular ones that are just kind of funky shapes that look like that. Like that's irregular. That's weird. What is that? We don't know. Yeah. And this is like a barred, this is a barred spiral, right? This is a normal and this is a barred. So this is kind of what we look like. We're a barred bulge. That's a bulge, whatever. So other galaxies, groups and clusters of galaxies. 2 million light years in diameter, contains 40 galaxies, including the Milky Way. What is this? All right, Caitlin. That's our local group. It's local to us. It's local because it's where we are. And then we have large clusters that may contain thousands to millions of galaxies. Some of them are elliptical. And then we have masses of clusters, sum total of the mass of all members of galaxies. Lots of stuff. It's stuff within stuff within stuff within stuff. Like the very end of Men in Black when they look into that little the little tiny marble on the cat thing, you know, it's there's galaxies and it just keeps going, right? It's like that. Stuff within stuff, like a Russian doll. And then we have clusters of galaxies that organize into larger groups. Anybody? Wait, you know, it's Liam again. Superclusters, large group, supercluster. That's easy, right? Okay, so this is where it gets into like astrophysics and business, but this is not on your exam, but you should know. Well, okay, let me put it this way. The formulas are not on your exam. The concept very well might be. So Hubble in 1929 used redshift data to show the universe was expanding. So the redshifts in spectra of distant galaxies and hence their speeds of recession are proportional to their distance. What do we call this phrase? Caitlin. Yeah, we're looking for Hubble's law. Hubble's got a law. That's what it is. And then who else? The fish has a law. And then what do we call the unit of measurement that we use to describe the expansion? James.
Isn't that your favorite?
Hubble constant. Okay, yeah. So remember, constants are things you plug into a formula like pi. Mm-hmm. And like, what did we have the other day? We had the universal gravitation, right? And Avogadro's number, right? It's a constant. It's something you plug into a formula and it makes it work, okay? So red shift and blue shift. Now we talked last week about the electromagnetic spectrum, right? And you've got visible light and you've got blue on one end, red on the other. Stop, Alex, Bailey, quit. So you can tell when the light coming from a star is becoming more red. It brings in that whole Doppler effect concept of like when you can, when you can hear a sound, you know, when you hear the sound of like a horn coming past, right? And it's because when it gets further away, it gets more compressed. When it's near you, it's more spread out. It's the same idea with the light waves. And that's how you, stupid bird. And that's how you end up with the ability to tell that the universe is expanding outward from the central point, because you can actually see changes in the spectra from the stars that show that they're moving. Very similar to Doppler effect. If you were to do an AP physics or college level astronomy, you'd be talking about this kind of stuff. So basically, these are the formulas. This is what our dude Hubble came up with. And you're able to tell recessional velocity, how quickly it is moving away, and the distance it is from you. And this also tells you, like, obviously the two are related, right? Just like you would expect. The farther, this is the farther it goes, this is the faster it goes. Well, where's it going? That's the line there through the center. So we have, keep that in mind, that it's redshift that's important. And if you understand how that works, that it's the shift in the spectra you're seeing, and it has to do with the change in the wavelength of the light, which is indicative of the distance. When you see that change, you can tell it's moving further away. So we have active galaxies. So what emits as much or more energy than the rest of the galaxy? Do we know? Anybody? Alex, do you know?
The center?
All right, yep, it's the nucleus, right? So that's the center. So your active galactic nucleus. And then what is very luminous, often elliptical, and emit more energy in radio waves than in light? Milo, did you know it? There you go, radio galaxies. Pretty darn cool. And then what is a star-like object? Emission lines in the spectra, very luminous, distant, and active. Caitlin. Quasars. Okay, yeah. All right, so you've got quasars redshift. And you can use a quasar redshift to infer the extreme distance of a quasar. Quasars visible today are showing their light from billions of years ago. They're very old. It took that long for the light to get to us. And AGNs and quasars, this is AGN, right? Active galactic nucleus, and quasars emit more energy than ordinary galaxies. So again, these are other things we can see if we study the sky long enough. All right, so cosmology is the study of nature, origin, and evolution of the universe. It's not cosmetology. There are people, like I said, we have a friend who in high school signed up for cosmetology because he thought it was cosmology. He had an interesting quarter. It was a quarter long elective. He had really interesting quarter. Oh, you know, this first one. Okay, so what's the idea that the universe began at a single point and has been expanding? All right, Caitlin, your hand was up first. That's your Big Bang. All right, get your bazinga, right? All right. So this is a model or a theory, right? And we talked about it. You get this cloud, right? And then it expands. I mean, it condenses on itself and then goes kaboom. We don't know where the cloud came from. We don't know where the stuff in the cloud came from. We get this string theory concept that there's one element that all the other elements are coming from. And they're like, it almost explained it like vibrating on a separate pitch. If you want to get real cerebral and real mathy, string theory may be your thing. That is very cerebral. Yeah.
One of the bottoms.
Oh, it sure is. Oh yeah, well, that's okay. So some possible outcomes. What expands forever because there's not enough mass to counteract the expansion by means of gravitational contraction? James, was that your hand? Yeah, open universe, the universe in general. Yeah, okay, so that's what we're dealing with. It's expanding and expanding. And here's the thing. Where's it going? Like it's not contained, it's open. It's just continuing to go. But what's it going into? Well, what's space? Here we are again. This is where you get, I'm telling you, this is where you start to mix in. Theology gets mixed in a lot with this kind of stuff because it's weird. Yeah, it's really, really, we're actually going to talk about that a little bit too in the context of some literature. But it's really interesting because you think about it and you're like, okay, so it's continuing to expand into space, but what's space?
Just a void.
But is there something in it?
No.
What's in it? It's not air. So
Dark matter.
dark matter, what is that? Here we are again, right? It's fascinating. It's fascinating. So this is open universe theory. And then there's another one that says there's sufficient matter in the universe to stop the expansion driven by the Big Bang and cause an eventual recollapse. What's that one? Do we know, Alex?
Like closed universe?
Yeah, basically there's enough matter. It's going to have enough mass that it'll get to a point where the gravity can't hold it, where it's no longer fighting gravity, and gravity is going to act on it, suck it all back in, right? And then it'll collapse again. And then the flat universe, which is off. That is the one that slows to a halt but never contracts.
Is it supposed to say gravitational attraction?
Contraction. You caught one, but you won't have time for brownies. But yes, good catch.
If I can find enough.
Good. Oh, look at you. You're like, if we find out.
That every.
Actually, it could be attraction. That's not incorrect in that space because gravity is attracting,
Everything defines.
which is causing contraction. So sort of models, the open one just keeps going. The closed one's going to get to a point where it's going to turn around and collapse on itself again. And then, yeah, is it what? Yeah, it would go and go. Yeah, that would be the idea. That is interesting. And then the flat universe, it gets to a point and then it just stops. Just kind of stops there. So these are ideas. All right, now this one's pretty. And this is interesting. For real, accidentally. That's kind of nuts. But that's just the case. Yeah. So they have this. Yep. Cosmic background radiation. So this is what they were hearing. Microwave radiation developed from electromagnetic radiation created by the cooling of the universe can be detected as a persistent radio background noise. And it is the microwave portion of the electromagnetic radiation spectrum. And we can tell that the rate of expansion is accelerating. So not only is it expanding, but it's expanding faster and faster and faster. So we think about our three models there. Okay, is it going to expand faster and faster and faster and get to a point where it can't expand anymore? And then it's going to suck back in on itself? Or is it just going to stop? Or is it going to keep going forever and ever?
Well, there's a theory that thinks of the first one said it goes out until it kind of like snaps back on into itself.
Yep.
And then restarts the universe as another Big Bang.
Exactly.
might be on.
There's
like,
other theories.
Yeah.
that It'll
Maybe our first
expand to the
maybe.
point where
Mhm.
light won't be able to be seen from between galaxies.
Yeah.
And that's gonna cause heat death of the universe.
We could be on universe iteration 45.
Great for
Beyond universe iteration 100.
Yeah, we have no idea. If that's the case, that could be what's happening. So contents of the universe is 21% dark matter, 75% dark energy. And the remaining part is everything else we know as matter. Everything else we know as what we see, feel, touch, evidence that we can hear because waves are passing through stuff. Yes.
Say that when they recorded the two black holes that collided with each other,
Mm-hmm.
they sent like a radioactive like a radio wave.
Yeah.
Massive radio wave.
Yeah.
In two directions, like a big beam.
Mhm,
Two directions,
mhm.
and it wouldn't be able to fly in our galaxy.
Yeesh.
It missed by like a couple million miles.
Well, thank God for that. All right. Now let's talk about something fringe and funky for a minute. It's still science, but we're talking the edges of science. So SETI is the Search for Extraterrestrial Intelligence. This is an organization of multiple scientists, right? And they work together in an effort, this came straight from their website, in an effort to detect evidence of technological civilizations that may exist elsewhere in the universe, particularly in our galaxy. There are potentially billions of locations outside our solar system that may host life. With our current technology, we have some ability to discover evidence of cosmic habitation, and in the specific case of our SETI experiments, to find beings that are at a technological level at least as advanced as our own. Yeah.
My dad was watching a video the other day that said there is most likely other life forms out there, but there's no way that we could get to them or they could get to us because they're like
So far away. Yeah.
So we have this, we kind of have a limit of how far we can see.
Mm-hmm.
And we haven't seen anything, which means they're most likely further away.
Right.
But the thing is, if they were to observe our planet from that much further
Mhm.
away, they would be seeing us as dinosaurs. The lights.
Because yeah, how long it takes for light to get there. So there's when you get into the whole time travel and light. How, if you travel faster than light, then you're gonna shift time.
also if we tried to send people on a ship
Mm-hmm.
to there, eventually people would enter.
Oh yeah, that's a very good point. Plus, you wouldn't. I mean, there's no way to make it. It would take too long. I mean, way too long. Yeah, royalty of Europe, European royalty. Yeah.
The precursor to Apple.
So on the topic of SETI, so this is a video from SETI's website, and they are legitimate enough to have a particular narrator who you'll recognize immediately. Yeah, how'd you know?
You have a fast type?
Yeah.
Let's go.
Carl Sagan again. Remember we talked Carl Sagan last week? We're gonna talk about him more in a minute.
Finding life beyond Earth is no longer the dream. It's a discovery that will likely be made during our lifetime. And it will change everything. We've been here for more than 36 years at the forefront of a quest that many consider science fiction.
Mars is the closest planet where we might find the possibilities of alien life.
We are home to over 100 explorer scientists.
It is incredible.
Our purpose is simple.
Just to understand what you have in your own backyard as you're looking up into the cosmos.
To understand the origins and prevalence of life in the universe.
What we are doing is to try to understand, are we alone in the solar system?
Why do we pursue our mission? Because the discovery of life beyond Earth will lay the framework for humanity's next steps to the stars.
We are trying to understand why we even exist.
We are the SETI Institute.
So I thought it was interesting because it's almost like they spent all their money on Morgan Freeman and then just got stock video for the rest of the thing. But hey, you know, whatever works. So
I'd say it's worth it.
I'm fine.
So here's this is some interesting additional enrichment stuff that I think is important. So we had a Carl Sagan quote at the beginning of that stuff about SETI. We talked about Carl Sagan last week. So Carl Sagan was a professor of astronomy and space sciences and director of the Laboratory for Planetary Studies at Cornell University. And he played a leading role in the Mariner, Viking, and Voyager spacecraft expeditions, for which he received the NASA medals for exceptional scientific achievement. Dr. Sagan received the Pulitzer Prize and the highest awards for both the National Academy of Sciences and the National Science Foundation for his contributions to science, literature, education, and preservation of the environment. His book Cosmos was the best-selling science book ever published in the English language. And his best-selling novel, Contact, was turned into a major motion picture. So Contact, has anyone seen it?
I think I.
Highly recommend. And I'll tell you why. It's a thinking movie. So you got somebody like Carl Sagan, who's you know, CV I just read for you. This guy is a thinker. This is a smart guy. So this is not a science fiction novel that is jumping the shark every 2 seconds and completely ridiculous. This is a guy who really for real thinks. So in the novel, as in the film, SETI, which is what the novel, the main character works for SETI, it's Ellie Arroway. And in the film, she's played by Jodie Foster, who's amazing, right? She detects a signal from the Vega system, and it contains the first 26 prime numbers. And it's interpreted as a sign of intelligent life. She later finds another message containing blueprints for the construction of a large contraption that they just call the machine. And the whole world kind of cooperates to decode the blueprints, build the machine, which they believe will allow humans to establish direct contact with the aliens in Vega. Okay, here's what's interesting. So you got Jodie Foster, who I said is really good. You also got Matthew McConaughey, who plays a character that she meets, and he's a man of faith. His character is a man of faith. And this is where you get theology. You said theology a bit ago. So there's like a panel, and they're trying to decide who gets to go in the machine. Like it had space for one human. So who gets to go in the machine? So they talked about it, and they were like, well, do we send a scientist? Do we send this? Do we send that? And in the end, a lot of stuff happens. I'm not going to ruin for you, but in the end, Ellie Arroway, it gets to go in the machine. But one of the questions that she's asked during this panel discussion is, do you believe in God? Because it came up that humans in general, most humans believe in something outside themselves, not all, but the majority. And the idea was, do we send somebody who doesn't believe in anything beyond herself to space? Is that a representation of us? Do we send this person to the aliens? Like, shouldn't this person represent humanity and how we feel, how we think? So that came up, all right? So keep that in mind, that there's this whole faith. And she says multiple times that, you know, her character bases her life on evidence because she's a scientist. So faith and evidence are two completely different things, right? Evidence you can see, you can test, you observe, and faith is something you have to take without any of that. That's the whole point of faith. Okay, so she ends up being the one to go in the machine. The movie starts with her as a little girl, and she's using shortwave radio like ham radio. And her mother died in childbirth, so she doesn't know her. And she learned how to do the ham radio stuff from her dad. So it starts, this is the very beginning of the movie. It's really a great movie. So these are all the radio waves, right? These things have gone out into space. If you listen.
Imagine they only going past this, be like, I don't want to go there.
So you notice we're going back in time. These are getting older and older, these radio wave recordings. Further you get away, more back in time. Earlier radio waves are further and further out. Do you hear Hitler right there? Mm-hmm. 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 And this dead silence is very effective for what they're trying to convey here. Mm-hmm.
This would have been cool.
Yeah.
This is W9GFL here. Come back. CQ. CQ. This is W9GFL here. Come back.
So her father actually dies too. And like, she spends a lot of time trying to, I mean, for real, sad, right? So she spends a lot of time trying to get in touch with him. Okay, so she gets all grown up. She gets all grown up and she's working for SETI and she's in Mexico and this scene occurs.
Arecibo, right?
Does it show?
Yeah. Correct, Jack?
No.
Mind if I sit down? I hear the locals, they call it El Radar. Convinced it has some dark military purpose.
I think we're pretty harmless.
Farmer Johnson,
Oh, no.
nice to meet you, Ellen. What are you studying?
Oh, the usual. Nebulae, quasars, pulsars, stuff like that. What are you writing?
The usual nouns, adverbs, adjectives here and there.
I work on a project called SAVE.
Search for extraterrestrial intelligence? Wow. And that is out there.
Wait, are you a student or something?
I'm writing a book, energy and research about how technology affects third world cultures. I'm also looking at this guy, David Drummond, he's the new head honcho of the National Science Foundation. I'm trying to get an interview with him. I take it you know him?
Mm-hmm. You can say that.
Steady, man. That's fringe. Crossed paths with this guy before. I mean, it's something like that. It's really chatted that, huh? Help us. Here you go.
Better keep this. Might save your life someday.
Will you have dinner with me tonight?
I don't make a very good research subjects. I'm just not gonna quote
No
them.
quotes, no quotes. It's got time. Good meal, good company.
There you go. But. Someone's coming in this Tuesday.
So, yeah, rejection, but you can already see like one literary, there's definitely some usage of symbol there, like what's he get in the Cracker Jack box? He pulled out the prize and he gave it to her. What was it? Y'all didn't catch that? He was eating Cracker Jack and he opened it up, he pulled out the prize and he gave it to her and she gave it back to him. It was a compass, a little compass. So think about like what a compass would mean as a literary tool, like you find your way, right? You always know where you're going with a compass, that kind of a thing. So this is the scene, sorry, where she catches the code coming in. Now this is important because, and she does explain it later in the movie, but what is the signal that's being sent that they're hearing? She's out laying in this field with this big array of dishes. And this is real, like that's a real picture of it. It exists. She's out there like laying on the hood of her car with big earphones on because you're listening for very faint sounds. And she hears it and comes running back to the lab here. And they realize that the sound that's being sent are pulses being sent as prime numbers. And that's important because math is a language in a way that is a universal language. Like math is math is math. Whereas all the other languages are not necessarily the same, but math is the same. So these aliens chose to communicate through math because it's a universal language. So she figures that out here, and the dudes that she's working with are obviously
Partially polarized set of moving pulses that modulates.
I love you too.
People across the board. They're on the way. 4.4623 gigahertz. In times pi. Told you. Wrong sucker too. I got it. I just did it. You hear? Be lying. Could be AWACS out of Kirtland jamming us, but I don't doubt it. Let's see if Bud's reading it too. Willie, give me the offense. Are we recording? Never stop. No. AWACS status is negative. What stands? On this frequency? No. Fine, come on. All right, not tracking any snoops in this vector. Shuttle nevers and sleep on it. Okay, point source confirmed. Whatever it is, it ain't local. I checked in the barometer somewhere in Lyra, I think. There you go. Yeah, babe. 26 light years away. Hey, what's the peak intensity? Coming up. There you go. Hey, a bunch of times there's sequence. I get the results always. Got it. We need over 100 Janet. Pick it up on my. All right, we're starting. Wait a minute, I think the numbers. There's 3. The one before it was 2. Base 10 numbers. Just start counting now. See how long we can get. 1. 7. 2, 3, 5, 7. Those are all prime numbers. And it's the actual phenomenon. Calm down and go to the door. It doesn't make any sense. The system is too young. You can't have a line that's with 40 million. Let alone lighting. Let alone well, maybe you can go up there, maybe they're just visiting. I don't know. Okay, so it's it would get clobbered. Well, not if they use certain laser blasters and photon torpedoes. Funny, well.
No, he's right. We go public with this, we're wrong, it's over. We're cooked.
Whatever the signal is, we better do something soon, Vegas is set. Deposition is confirmed, we've got 4.4623 gigahertz. Confirmed, we've got 112 jam keys.
Have you had a source location yet?
We put it right smack in the middle. Vega.
Okay, thanks, Ian. Just keep tracking and we'll get back to you.
Yeah, righto.
The Australians.
Yep.
The Australians.
Opposite side, so as it sets, they can pick it up right on one side of the planet and then the other.
Okay. Come on, we'll see every pump bridge with two and
Yep.
I'll do one. We're gonna call now.
Everybody, she says. So clearly, they've proved something's up, okay? They've proved that something's going on. No way there's something not going on, prime numbers. Okay, so this encrypted signal went open when they finally figure it out and everybody agrees they're hearing something and everybody starts listening. There's this plans for manufacturing of this enormous machine here, okay? This is the machine. And it's presumably gonna take somebody to talk to the aliens. That's what they're thinking. Right? So that's what the machine looks like. So they figure they're gonna build this thing and send somebody to go talk with these aliens. So this is Roger Ebert. I got this from Roger Ebert. You know who he is? He's a movie critic, like one of the most famous. Siskel and Ebert used to do all the movie critiques. So anyway, he says, I will not describe what happens to Ellie after she takes the trip. There was much debate at the time about whether she, in fact, ever left Earth. Although a line of dialogue about 18 hours of static seems to be significant. The more you think about it, the logic involved, the more fascinating the movie becomes. The original signal received from space is the first television signal ever broadcast on Earth. And since we know when that was, we know how many years it would have needed to make a round trip. So they send back to us our first television broadcast. One of the things that they see when they put all the data together on the screen, one of the things they see is like they zoom in and they're like, what is that? And it's a swastika because it's World War II stuff. And that's some of the first stuff that came out. And that's what they're seeing. And they're like, oh God, like that's what the aliens are seeing of us. That's not great, right? But the aliens don't know. It's just, look, I'm paying attention. So she ends up being the one, like I said, to get in this machine. And if you look right here, you'll see this little, I'll make that go away for a minute. Go back here. If you look, you see this little spot here? There's like a little capsule and one seat in the capsule. And there were no instructions for seat belts or anything of the sort, just a seat. But she got in there and they had put in seat belts because they're like, well, duh, we're not gonna like put you in there without seat belts. And the idea is that that little capsule is gonna drop and go into this machine and then something's going to happen. For the observing world, everybody that watched, the capsule fell and went smashed down into the water below, and that was the end of it. But her experience was 100% different. In the little time that it took her to fall, 18 hours of static was recorded somehow. So yeah, so this is where it gets real interesting and thinky, like I said. So, did I have a,
Show us
hang on.
how humanity really
I have it. Whoop. So anyway, it is completely worth watching. Totally recommend it. And in the end, there is a court scene where they bring up the concept of Occam's razor. Does anybody know what Occam's razor is? Do you know? Do you know what it is, Alex?
The simplest answer is most often the.
Yeah,
correct.
the simplest answer is most often the correct answer. Like, don't overcomplicate things. And they bring up Occam's razor to her, and here she is, she's based her whole life on evidence, 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 right? That's what she says she's all about. And the only evidence we have is she dropped from that thing and fell through. But she claims, I don't know what that's about. She claims this whole experience. I didn't know he was in the front yard. Oh, that's frightening. I bet the wind blew a gate open. Can you check, please? Thank you. I was just looking for my clicker and I don't know where it went. The boy for coming home. God knows where he went. So anyway, she's asked, do you know, Dr. Arroway, do you know what Occam's razor is? And she's like, yes, the simplest explanation is usually the truth. And they're like, so what's more likely? You fell through here, maybe had some kind of mental event, or you actually went somewhere and had some experience. And here she's faced with she's in the position where she has to explain something she can't prove, and there's no evidence for it. But for her, it was very, very real. And that's where the theology comes in. It's the whole argument that this movie, it's a really fascinating argument. It's really, really interesting. So this one's a little treat, this next bit. So this is the Falcon Heavy that went up on Sunday night, carrying Viasat 3. Now, when it went up, unfortunately, they had to burn a little more fuel than they had necessarily planned. I mean, they planned for it, but their goal is to have the solid rocket boosters return. They don't always return. In this case, they didn't. They had to go ahead and just blow them up like they did with the one last week that cartwheeled all over it, right? That was fun. But that's because they had used a little more fuel with the launch than they'd planned, so there wasn't enough to land them properly. Now, like I said, we have a real good friend who's now moved there, and she's standing in her driveway. This is the coolest thing. I would get a lawn chair and just sit myself out there every time. The entertaining thing is her 5-year-old daughter's commentary. So you have to listen, like you can't talk over Maddie, because Maddie's commentary is just simply amazing. And at one point she asked so many questions that you can hear our friend Jen say, I don't know, I'm gonna have to ask Jason, because my husband's the one who told her, get outside, you gotta go see this. And this is the second one they'd seen. The other one they'd seen had gone a different direction, another rocket launch. And it's all the trajectory matters and where they're going. But it's just totally fun.
I see it. It's way across.
Yeah.
You see that white?
Yeah.
That's it.
Yeah.
I know.
That's it.
I know. Cool is that? Looks like the sun in the sky, doesn't it?
Yeah. But Daddy, Mommy, maybe we should stay out here for a little bit, Daddy, to see the part come back down.
It's fine, a little bit different than last week.
They're great.
Watch this, if you do it, if I watch my eyes. And then that comes up.
Isn't that cool? Yeah.
See the smoke that came out of it.
I know, right?
Why is it going? It's going in.
It is going a different trajectory, it looks like, right? Than last time?
The other one is like up, straight up.
Now they can hear it. Took a while.
Oh, you can hear it now.
Hear it? They couldn't hear it before. It took that long for the sound to get to him. You could feel it.
What can you feel, Maggie? Say it louder. So the earth did what? Earth was shooking?
Yeah, that's what happened.
The earth was shooking.
I felt like I could
Flash. That's the only way.
Yeah, it should have been. That's weird. Okay. And it looks like it's going like this, right? That's the curvature of the earth.
Don't really know. I gotta ask you. Or I gotta ask Elon Musk. I gotta look it up.
That's just the curvature, because it was sent at an angle like this, not like that. So you can see the curvature, which is really kind of cool. She was fascinating and the cutest thing ever. She was talking to us in the driveway. She was chit chat and she's like, why is it doing that? That is the coolest thing. Why is it doing that? So, and she told us that they had some like International Women's Day thing at her preschool, and she got to dress as Katherine Johnson, and she wanted to know if we knew who Katherine Johnson was, and we're like, yeah, she was a computer for NASA. Oh yeah, and she told us all about Katherine Johnson. So earth shooking. Earth shooking. I love that. The earth shooking. That was the best. Earth shooking. Yeah. I told Jen, I said, I'm going to come down and kidnap her just so you know. Well, I'll show you real quick and then we'll be done, but I'll show you.
Don't worry about it.
She's right? Like I'm going to, because she's super cute. Real quick. Oop. Boop, boop. All these things are in my way. I'll show you. I'll show you, Maddie. And then y'all will be good to go.
Shot spaceship.
Yeah, just shoot spaceship and then.
What?
big red flag.
No, there's always Ozzy. Yeah, that's me. Where, yeah. Do. Oh, that's Lucas. That's the little one. This is Maddie. This is our narrator. So she's the cutest freaking thing. Anyway, so be sure before you get here next week that you have reviewed all the stuff for the exam. Keep in mind that everything that is going to be a question of sorts is on the Jeopardy, but stuff like images and anything that's visual is going to be a good thing to look in the PowerPoint for. Okay. And I will turn this to give you coins. And there's like 9 minutes, so you have some time to get your goodies. And I will stop the share for Parker. Bye, Parker.
I can already put it in my head.